Good morning, everyone. I hope you're all doing well. So we're gonna today talk about power, work, and energy. So let's start by defining what the power of a force is. So power. So we're introducing a few definitions here. Okay, so that's by definition the power of a force. So the power of a force F acting at a particle with mass m plus cv is F dot v. So the units of that is newtons times meters per second or watts. Now the work of a force is the integral of the power with respect to time. And that's a definition, by the way. Work. So the work of the same force F in the interval t1, t2 is the integral of the power with respect to time. Okay, so that's by definition what the work of a force is, the integral of the power with respect to time. So I can replace the power by what it is, F dot V dt. Now, what is this V dt term equal to? Not ds, but close. What is it? dr, right? dr. Remember, because v is dr by dt, so dr is v dt. So I can change this integral from being written in an integral with respect to time to an integral dr. And now once I have an integral with respect to dr, I have to change the boundaries. These are going to be values of r. So that's going to be r of t1 and r at t2. Have we seen this sort of integral before? In calculus, maybe? What was it called? A line integral, exactly. So that's a line integral. So then this dr, we can express in the different coordinate systems, right? So this is a differential. R in Cartesians, R is x ex plus y ey plus z ez. So what is dr in this case, expressed in this Cartesian coordinate system? Yes?
Dx plus dy plus dz.
Right, what about the basis vectors?
Dx dy.
Exactly. So dx ex plus dy ey plus dz ez. Okay, so that's dr in Cartesians. Now take a minute, calculate dr in cylindrical polars and in the Serif-Renyi basis. So that's for Cartesians. What about for the cylindrical polar? R is RER plus ZEZ. And for the Serif-Renyi basis, V is VET. So again, the question is, what is dr expressed in each basis? And as a hint, this expression here might be helpful, that dr is equal to VDT. So take a minute, chat with your neighbors. What is dr? Think about it. What is dr expressed in each basis? Okay, so what do we think? What is the r expressed in the cylindrical polar coordinate system? That's v, not dr. To be able to get dr, I have to multiply it by dt, right? So what will I get? Dr er plus dzz. Is that it? R d theta, yeah, right. Yes, so you learned in calculus how to take the differential of a quantity, and then the shortcut is you can calculate v and multiply it by dt, you can get dr. Okay? Now, what about for the Serif-Renyi basis? What is dr equal to? Why don't I just write? I'll take v and I'll multiply it by dt. So that's v dt, which is VET multiplied by dt. V dt. And what is v dt equal to? What is it? ds, right? Because v is the speed is ds by dt. So that's ds et. Okay? So let's repeat what have we done so far. We're introducing the power of a force, which is the force started with the velocity of the particle. The work of a force is the integral of the power dt, which I can write this integral as an integral with respect to dr, a line integral. And I can evaluate the integral in any coordinate system I want. Namely, we've talked about the expressions of dr in Cartesian, cylindrical polar, and the Serif-Renyi basis. Does that make sense? Any questions so far? Questions? Okay. So this integral is path dependent, right? It depends on dr, the path. So it depends on the path traced by the particle. In which situation would the work of a force be 0? This means that the work of the force between 2 times is equal to 0. When would a force be workless? Under what conditions? Yes, so what would need to be perpendicular? Exactly. So if f dot v are perpendicular, dot v equals to 0. In other words, it's f is perpendicular to V, the force is perpendicular to V, the velocity or the force is perpendicular to the displacement, then the force is workless. Can we think of an example where the force, or if a certain force acting on a system would be workless? What is it? The normal force in which situation?
When an object is just still.
Right. So if I have an object such sitting still on a surface, well, it's not moving, then the work is zero because there's no displacement or there's no velocity, right? So that's another case where the work of a force is zero. If V is equal to zero or dr is equal to zero, then F is workless. Okay, so by this definition of the work of a force, if I have this desk and I'm pushing it and the desk is not moving, what is the work of the force I'm applying on the desk? Am I doing any work? No, I'm not doing any work because the desk is not moving, right? So by this definition of the work, if there is no displacement, then I'm definitely not doing any work. Now, think of me right now pushing this cell phone on the desk. Am I doing some work? Yes, because the integral of f dotted with the velocity of the phone is going to be non-zero. However, is the normal force acting on the phone doing any work? No, because what's the direction of the normal force? It's perpendicular to the surface, and what's the velocity of the phone? It's along the surface. So the dot product between the two is going to be zero. They're perpendicular, so the normal force is workless. What about the weight force in this situation? Is it workless? Yes, because it's also vertical whilst the displacement is horizontal. Okay, now let us think of a projectile motion. Is the work of a force zero during projectile motion? Work of the weight, right? If it's a projectile and then the only force acting on it is the weight. Is the work of the weight zero? No. Is it going to be positive or negative, the work of the weight? So what is it going to be? The sign of the work of the weight during projectile motion. Depends on which angle. Okay, so the trajectory is going to be parabolic, right? This is the trajectory of the particle. And the weight is always acting vertically downwards, right? Now, is the work of the weight going to be positive or negative? Think. What is it? Negative, then positive. From where to where is it going to be negative? Right, so the work of the weight from initially to the apex, the work of the weight is going to be negative. And what about in this region? The work of the weight from like 2 to 3 is going to be positive. Raise your hand if you agree with this, and then you have to think of a reason to justify it. So chat with your neighbor, do you agree, and then why? Why is that the case? Okay, so what do we think? Do we agree? Raise your hands for yes. Okay, cool. Why is it? Why is the work of the weight positive or negative as I'm going up? How is the weight pointing? Down, right? How is the velocity of the particle pointing? Upwards. So if I take the dot product of the weight and the velocity, the dot product is going to be positive or negative? Negative. And integrating a bunch of negative quantities, which is basically summing them, I'm going to get a negative work. Does that make sense? What about when the particle is going down? How is the weight pointing? Down. How is the velocity of the particle pointing? Downwards, too. So the product between these two is going to be positive. Integrating that is going to give us a positive quantity. So then the sign of the work, if the force and the displacement, if their dot product is positive, then the work is going to be positive. And if their dot product is negative, then the work is going to be negative. So for example, if I have a box and I push it, a box of chalk, and I push it on the table, what is the work of the normal force acting on the box during its motion? The work of the normal acting on the box during its motion, 0. What about the work of the weight? 0. What about the work of the friction force? Not 0. Is it going to be positive or negative? Negative. Why? It's going to oppose what? The velocity, right? Very good. Any questions? Okay. So let's think of an example. Consider two smooth rails. Okay, so I have 2 points, A and B, and in one case they're connected by a straight path, straight rail, and in another case they're connected by some curved, randomly shaped rail, and I have a particle that's traveling from B to A. Now I want to calculate the work of all the forces acting on this particle during its motion from B to A. What do I do? Free body diagram, exactly. First I have to determine all the forces acting on the particle, right? So I have the particle. What are the forces acting on it? Weight, vertically down, and a normal force, right? Okay. Now, any other forces acting on the particle? Now I want to calculate the work of all the forces acting on the particle as it goes from A to B. So that's the work of the weight from A to B, plus the work of the normal force from A to B. Now if I want to calculate the work of the weight from A to B, I'll use the definition of the work of a force. So that's the integral of the weight dotted with dr from RA to RB. With me so far? Does that make sense? So this first portion is the work of the weight. The second portion would be the work of the normal force. Okay. How can I say mathematically or justify mathematically that the work of the normal force is going to be 0? What is the direction of the normal force going to be? Right, perpendicular. If I use the Serif-Frenet basis, what are the components of the normal force going to be? EB and EN, exactly. NN EB, NN EN plus NB EB. Remember we talked about a particle moving on a curve, then it has two independent normal force components. It's like you being on a roller coaster. There should be a normal force from the sides of the roller coaster and from below to keep you on it. Now dr, what is dr in the Serif-Frenet basis? From here, dr is equal to dSET. Notice how ET is perpendicular to both EN and EB. So what is the work of the normal force here? 0. Okay. Now for the work of the weight, it's a different story. Well, the weight of a force, how can I evaluate this integral? Any ideas? Any ideas on how to evaluate this integral to determine the work of the weight? Right, so the weight is minus mg Ez. So is that force, is it going to change throughout the path of the particle, throughout the motion of the particle? No, right. The weight is a constant force, right? The weight is a constant force. So being a constant force, I can take it outside the integral. I'll get the weight dotted with the integral of Ra, Rb, dr. And what's this integral equal to? Well, it's the integral of dr, which is r, right, from the fundamental theorem of calculus. So this is just r evaluated between Rb and Ra. So that's, ran out of space here, W dot Rb minus Ra. Okay? So it's an interesting thing to note here about the work of the weight, that does it depend actually on the path of the particle? No, it doesn't. We're going to see why. It's a special kind of force whose work does not depend on the path of the particle. But for now, that would be the work of the weight, and it would be the same in both cases for both rails, right? As long as Rb minus Ra is the same, right? Rb minus Ra is which factor? This vector Rb minus Ra is which factor? If I want to draw it on the figure, it goes from where to where? From A to B, exactly. Okay, very good. Any questions? Okay. Question. Any questions from your side first? Okay. Is the work of the normal force always 0? Is the work of the normal force always 0? No. Can you think of a situation where the work of the normal force is not 0? Yes. Exactly. If you are in an elevator that's accelerating upwards or downwards, so if you have a particle in an elevator, that's the normal force acting on the particle. And as long as the elevator is moving, the normal force started with the velocity of the particle. Would that be 0? No. So that's right. A classical example of the normal force being workless is that of a particle in an elevator. And it doesn't have to be accelerating, it could just be moving. Great. Any questions? Questions? Okay, let's introduce one more definition, kinetic energy. Raise your hand if you've heard of kinetic energy before. What is the kinetic energy of a particle? Yeah. It's a scalar. It's calculated by half mv dot v. And I can express that in different coordinate systems. So t is equal to half m x dot squared plus y dot squared plus z dot squared. In Cartesians, half m r dot squared plus r squared z dot squared plus z dot squared in cylindrical polars, which is equal to half m v squared in the Serif-Renyi basis. Okay, if we've seen kinetic energy before, then we've probably seen the work energy theorem. So let's introduce it and derive it. Okay, so the work energy theorem says that the rate of change, it says that the rate of change of the kinetic energy acting on the particle is the power of all the forces. The rate of change of the kinetic energy acting on the particle is the power of all the forces, which is F dot. Okay. So the work energy theorem, maybe you've seen it in a different form. Maybe you've seen the time integral of the work energy theorem, that the kinetic energy between 2 points, Tb minus Ta, is integral of F dot V dt from T1 to T2, which is the work of the forces from 1 to 2, right? So maybe you've seen it in this form. The change in kinetic energy of a particle is equal to the work of the forces acting on it. And now this work energy theorem is not an independent law like the balance of linear momentum, which we cannot prove. The work energy theorem we can actually derive from the balance of linear momentum. So this is derivable. The derivation is quite simple. So I'll start with F equals ma, or F equals, ma. What do you think I should do next? Any ideas? Yeah, I'm going to dot to this equation with V. So F dot V is equal to m A dot V. So this F dot V term recovers the power of the force, right? So this is P. So then, can I show that this is T dot, the rate of change of the kinetic energy? So if I have that T is equal to half mv dot V, how do I calculate T dot? That would be equal to what? The derivative, which is what? Half m. Right. So that's twice v dot v, so I'll get m v dot v, which is ma dot v. So this is indeed T dot. And that's it. That's the work energy theorem proved. Again, if I integrate this with respect to time, I'll get this form. Okay? Okay, any questions? Let us go back to the projectile example. Okay, for the projectile example, if you want to apply the work energy theorem between points A, B, and then BC. Between A and B, we said that the work of the weight, the work of F, which is the work of the weight, is going to be negative, right? The work of the weight from A to B is negative, whereas the work of the weight from B to C is positive. So what is happening to the kinetic energy of the particle as it goes from A to B? It's going to decrease. Why? Right. So if I apply the work energy theorem, the kinetic energy at TB is equal to the kinetic energy, or the kinetic energy at TB minus the kinetic energy at TA. So the change in kinetic energy between TB and TA, which is going to be the work of the weight, is going to be negative. So the kinetic energy is going to decrease, which is what happens, right? You start with the kinetic energy that's some initial value, and it goes to 0 at the apex, and then as the particle goes down, it gains kinetic energy. Okay? So let us do an example here. The printer was not working today, so you're going to have to open set 11 on your devices. So set 11, problem 2. So take 10 minutes, work with a partner to solve set 11, problem 2. I'm going to draw it on the board in the meantime. Okay, so I'm happy to answer any questions. Work on this until we get the final answer in the final answer presented. And just go ahead and do part B, where P is 40 newtons. Any questions, anyone? Do you have pen and paper? How are you working?
The normal force of this object, would it be opposite to the machine force, or should it be like the horizontal?
Oh, we don't know. You have to solve the problem to figure it out. But you might not need to know how it points after all. So. Did anyone get the final answer yet? So which equation are we going to be applying here? The work energy theorem. I think we're going to use the integral form, the one in the boxed work energy theorem between the bottom point and the top location of the box, right? Any questions?
I'm not really sure where to go from this because I found out as much as I could, like the distance from
Mm-hmm.
the force, but I'm not sure.
So how many forces are acting on this particle throughout its motion? three: the weight, the normal, and the force P, right? And we're using the work energy theorem. So that's going to be, call this state AB. TB minus TA is the work of all the forces, which is the work of the weight, plus the work of the normal, plus the work of force P from A to B, right? And now you need to find each of these terms individually. So how would you find the work of the weight? How would you find the work of the normal force? How would you find the work of P? How would you find the work of any force? You have to go back to the definition of the work of the force. Okay, giving that a couple more minutes. I'm good. How are you doing? How's the problem going? Where's your pen and paper? How are you writing? Where's your pen and paper, sir? How's it going? Okay, let's solve this together. The next one is going to be a quiz. So, the 2 kilogram collar is at rest in position A when the constant force P is applied as shown. Determine the speed of the collar as it passes point B. So, what is the kinetic energy of the collar at A if it's starting from rest at A? 0, right? The velocity of the particle at B, the speed of the particle at B is what we want to calculate. So TB is going to be half m, the speed of the particle at B squared, which is what we want to calculate. What is the work of the normal force acting on the particle throughout its motion? 0, why? The normal force is always perpendicular to the trajectory, the displacement. Okay, very well. So that's 0. What about the work of the weight? I have to go back to the definition of the work of the force. So that's the integral of the weight dot dr going from Ra to Rb. And as we did before, the weight is constant force. So I can take it outside and I'll get W dot Rb minus Ra, right? What about the work of the force P? How do I calculate that? Same way. So that's the integral of P dot dr from Ra to Rb. So P is also a constant force, so that's just P dot Rb minus Ra. Right? What is Rb minus Ra in this problem? What is it? Rb minus Ra is equal to what? 0.8 ex plus 1.6 ey. Okay, what about the weight? Negative mg ex. What about P? It's whatever it is, 40 cosine 35 ex plus sine 35 degrees ey. Right. Thank you. Okay. And then you have everything you need to replace in the equation and calculate VB, right? Any questions? Raise your hand if you were almost getting there. Yeah? Great. Okay. Very good. So then notice that there are some forces, like the weight, like this force P, whose work does not really depend on the trajectory, it only depends on the endpoints of the path. So you've learned about this or in calculus. I think in multivariable calculus. The notion of calculating a line integral of a force dotted with or a vector dotted with dr, and under what conditions is this integral independent of the trajectory or independent of the path of the particle. Does that ring a bell? Yes.
Is it when RA and RB are the same point?
Well, if RA and RB are the same point, not necessarily. Not necessarily. Yeah.
I don't remember this specifically, but something about the gradient being smooth or.
The gradient, it has to do with the gradient. So what is the gradient? It's an operator applying on a scalar to give us the gradient of a function is going to be a vector, right? So any scalar function can give us a vector. By taking the gradient, we can get a vector. But does every vector field, is it always derivable from a scalar function? No. Right, so every scalar function, I can take its gradient, I'll get a vector field. Now, every vector field, is that derivable from every vector field? Does that come from some scalar function? Not necessarily. Under what condition is a vector field derivable from? We call it a potential. There are conditions that you probably learned about. So, I'll erase here, or I'll erase here. Okay. Okay, so I can have a scalar function, f is a scalar function. I can calculate the gradient of f. And that's going to be a vector. And by definition, the gradient of f is such that df differential is equal to gradient of f dotted with dr. So I can calculate the gradient of a function in different coordinate systems, right? So what is the gradient of a function in Cartesian coordinates? Right. So del f, I can write it as del f by del x, ex, plus del f by del y, ey, plus del f by del z, ez. Raise your hand if this kind of rings a bell. Great. Right? Because df, I can write that as del f by del x dx plus del f by del y dy and del f by del z dz. So can you, and dr in Cartesians is dx ex plus dy ey plus dz ez. So can you confirm that gradient f dot dr is equal to df? Can you confirm this? Do you see it? So this expression can actually be taken to be the definition of the gradient of a function. So the gradient of a function is defined such that this happens, and this way the gradient is defined in any coordinate system. Now, from any scalar function f, I can obtain a vector field v. Okay. However, not all vectors are derivable from a potential. Okay. When they are, we call them a conservative vector field, and the function that they're derivable from is called the potential. If a vector field v can be written as the gradient of some function, some scalar function f, meaning that v is equal to gradient f, we call v a conservative vector field. And we call this f the potential energy function, or the potential function. Potential energy comes in dynamics. Potential function. Okay, any questions so far? So you've probably seen this before, and the conditions for a function to be derivable from a vector field, maybe you've showed it, it should be that fxy and fyx or something should be equal. And then there are three conditions, partial derivative needing to be equal. For a vector field to be derivable from a potential. Any questions? Questions? Okay. Now the question is, then why do we call V a conservative vector field in this case? What does conservative mean? Yes.
Is it that you can travel like kind of like up and down the gradient without and like be able to return to the same spot?
Maybe not sure. Yes. What is it? Yeah, so maybe close to what your friend has mentioned. So we'll think about it. But a conservative vector field kind of implies that there's something that needs to be conserved, a quantity that will be conserved. So let us go back to dynamics. If force is conservative, then it's derivable from some potential energy. Okay, so this is the symbol for a conservative force, F conservative, and it's derivable from a potential energy, meaning that it's the gradient of U. U is the symbol for potential energy. And this minus sign is a convention in dynamics. And you're going to see why we put it. Now, let's calculate the work of a conservative force. So I'll calculate the work of a force by the definition is the integral of the conservative force dotted with dr from R1 to R2. With me so far? So now I'm saying, okay, what if the force that I have is conservative, meaning that it's derivable from a potential? Well, in this case, I want to calculate the work of the force and see if I have any simplifications. So instead of the conservative force, I'm going to put that it's derivable from a potential. So it's going to be the gradient of some potential function dot dr. Okay. Raise your hand if you're with me so far here. Okay, great. Any questions? So then, questions. If I look at the gradient dot dr, what is this supposed to equal from the board above it? Yeah, what would that be? du, exactly. From this, up there. The only difference is the minus sign, which we add in dynamics. We'll see why. We add it by convention, but that's the integral of du. And since I changed the differential, I'll put it from, du of r. Oh. Well, du of r. From R1 to R2. Okay? So this is just U2 minus U1, where U2 is evaluated at R2 and U1 is evaluated at R1. So then, yeah, U2 is evaluated at R2 and U1 is evaluated at R1. Okay? So what have we learned so far? If a force is conservative, meaning it's the gradient of some scalar function that we call the potential energy, its work only depends on the endpoints of the trajectory, right? So we don't actually have to evaluate this long line integral to calculate the work of a conservative force. I can only look at the potential energy evaluated at the trajectory. Now, going back to the points made by your friends, if the trajectory is such that R1 and R2 are the same, what would be the work of the conservative force? 0. If you go back to the same place, the work of the conservative force is 0. Okay? Now, there are 3 types of conservative forces we will learn and use in this class. The first one is any constant force is conservative. Any constant force, we can show that it's derivable from a potential. The second one is the spring force. The spring force is also derivable from a potential. And the third one is the gravitational force, which is also derivable from a potential. So I'm just going to introduce these forces and their potentials here. But you're going to, if you look at the notes at Appendix A, I think it's Appendix A, one of the appendices, you can see the derivation of how I can derive each force from its potential. Okay? So in this class, we care about 3 types of conservative forces, or three conservative forces. So force, and its potential energy. Okay, so any constant force C which includes the weight. So any constant force C is a conservative force, and its potential energy is equal to minus C dot R. Okay, so the work is gonna be equal to minus U2 minus U1, or U1 minus U2. So U1, the work, is gonna be equal to U1 minus U2, which is minus C dot R1 minus C. So these minuses are all confusing. C dot R2, which is C dot R2 minus R1. Do I have some example of this? I erased them all. But if you go back and you look at where we calculated the work of the weight, for example, this expression should apply. Okay, does that make sense? Any questions? So you can look at the derivation in the notes. The spring force is a conservative force. Right, this is the stretch of the spring. So the spring force is conservative. The potential energy is half k epsilon squared. So the work of the spring force is going to be U1 minus U2, which is half k epsilon 1 squared minus epsilon 2 squared. The last one is going to be the gravitational potential energy. I'm going to copy it, I'm going to explain it. Okay. Oops, no, that's not what I wanted. Okay, so this gravitational potential force, it was proposed by Newton, its prescription was proposed by Newton, and it's the force between two bodies of masses m1 and m2. So okay, so if I have two bodies of masses m1 and m2, they're gonna exert forces on each other. So the force that m1 exerts on m2, for example, or the force m1, m2 is gonna try to pull m1 towards it. So it's this. F2 on 1. F2 on 1 is proportional to the two masses, m1 and m2. So the bigger the two masses, the bigger the force between them. G is a gravitational constant. And its value is 6.67. 408 times 10 to the 11 minus 11 meter cube kilogram minus 1 is minus 1. Okay, so the gravitational pull between the two particles is going to be proportional to their masses, inversely proportional to the distance between them. And guess what the direction is going to be? The force on M1 is going to be towards M2, right? So that's going to be R2 minus R1 over the magnitude of R2 minus R1. Okay? So this is a prescription proposed by Newton. Now, let us think of a particle and the Earth. A particle and the Earth. So this is the Earth. The mass of the Earth is going to be m Earth. This is a particle of mass m at a certain height h from the surface of the Earth, and that's the radius of the Earth. Okay. What is the pull of the Earth on m? What is the pull of the Earth on M? Guess which equation I'm going to apply? This one, right? This one. Okay, so the pull of the Earth on M is going to be G. What is M1 here? That's going to be M, right? What is M2? The mass of the Earth, exactly. Over the distance between the two particles, between the two centers squared, which is going to be equal to what? Radius of the Earth plus the height squared times a unit vector pointing towards the center of the Earth, from the particle towards the center of the Earth. Okay. So let us assume this. If the particle is very close to the Earth, such that the height of the particle relative to the Earth's surface is much less than the radius of the Earth. This term is going to approximately be equal to what? If h is very small relative to the radius of the Earth. Mm-hmm. So I'll be able to get rid of this h, right? Can anyone guess what the value of this would be? Yes. So that's 9.81. Okay? So that's where we get our gravitational force between an object and the Earth. Okay? Does that make sense? Any questions? Okay. Then you have a 5-minute break, and when you come back, you're going to have a quiz, which is going to be let me figure out which problem. Problem 3 in this set. Okay? Okay, so this quiz you should do individually. I'm happy to answer questions, but you should do it individually. You can chat with your neighbors, but you need to submit it on your own. Okay. I'm happy to answer any questions. Where's your solution to the quiz? Are you working on it? So the first step is always to draw the free body diagram to figure out all the forces acting on the system. And then you can set up the work energy theorem. Okay, if anyone has any questions, just let me know.
It says it's the velocity as it strikes the spring. Are we assuming that it's right before? Or
Yeah, right before. That would be right before. Yes.
I don't understand, like, if we set up the force equations, how
Oh, you're gonna use the work energy theorem to solve this problem. Yeah. Because usually you would set the force equation, you will get a differential equation of motion, and then you're gonna have to solve a differential equation between 2 points. Or you can apply the work energy theorem between 2 points.
this.
Hmm.
Then, like, we still need the normal force, right, for
Yes, then you have to calculate it from the balance of free momentum. Okay, what if you set your axes one along and one along the incline, one perpendicular to it? Then the acceleration is just in this direction.
given a coefficient of time,
Yes.
So we're also since we're given the constant friction, we have the surface friction.
You have constant friction?
Yeah,
Okay, is it static or kinetic?
it's kind of because it's moving.
Right, and what is it equal to then?
The equation. Okay.
Minus mu k n times v rel. Okay, yes, then what's your question?
Just wanted to make sure you understand what force is essentially.
Oh yeah. So normal weight, friction, and spring force when you hit the spring, yeah. work energy theorem?
Trying to.
Okay, where's your equation?
This is what I've got so far for the
Work of the weight
work of the weight and then work of
for the friction force.
And then this one's negative.
Wait, so how come you were able to remove the integral here?
For I haven't got to that part yet.
No, but here, like here there was an integral, and here it's not anymore.
That's right. Because is friction. Okay, so I was trying to go off of the fact that the weight is conservative, so you can
Right.
get rid of the integral there.
No,
Yeah.
but you cannot get rid of the integral because the weight is conservative. Because it's constant, you can.
Okay.
Or because it's conservative too. Yeah.
Right. Because we just said that.
Then you'd be applying the work of the weight would be that formula up there. Because the weight is
Right,
the
right.
constant force. Okay, but friction is not conservative.
Friction. Okay. Okay.
Then you
So
need to find what the friction force is, and then evaluate the integral.
friction force would be. Well, wouldn't
What is it,
because
static
the
or
friction
kinetic
force,
here?
it's kinetic, so it'd be.
Yeah.
I don't know what's that.
Minus mu k
Yeah, but it'd be.
m
Wouldn't it be like this, the normal force, and then the constant k, but the normal
magnitude
force
of the normal
is,
force.
magnitude. Sorry,
Yeah, and the direction opposite to the velocity.
direction. So negative.
Yeah, so it might be easier for everyone to put like an ex along the incline, ey perpendicular to it. Ex along incline, ey perpendicular to it, so that the motion would be along ex. Yeah. Mm-hmm. Yes. Well. Okay. So the friction force. Okay, so this is gonna be okay. If ex is pointing down, the friction force is along minus ex, right? Yeah. Then dr is a vector, which you can now write as dx ex, and then you can get rid of the. To get rid of the dot product, get rid of the ex. Okay. So it's like systematic. Write it and then I'll see.
So once you have a
What do you think it is? That's for the diffraction? What exactly do you want? What do you want? The spring force, the potential energy, or the stretch? Okay, the stretch. What is the stretch? It's the current length minus the unstretched length, right? That would be the stretch. We call it epsilon. The current length minus the unstretched length. how did you calculate the normal force from F equals MA?
F equal. So it's mass times the gravity, and then since we chose EX to be perpendicular to the bar,
Mm-hmm.
it's sine 60, and then time multiplied by.
Are you sure it's sine, not cosine?
Well, it's shouldn't be sine because we're trying to find the component that offsets the weight. So it would be
You're projecting along which direction?
because the normal force is supposed to be
Yeah. I'm not convinced yet. Is it sine? Is it cosine?
it should be sine
Why?
because if this
What, the horizontal component?
yeah, because that's what's going to be offset the weight.
So what is the horizontal component of the normal force?
Horizontal force should be sine.
No, I don't think you want the horizontal component of the normal force. Write F equals MA for the box, and then from there determine the normal force.
But then for the second.
Any questions?
I think a slightly different answer than the thing, but I'm not sure if it's rounding error or if it's actually I missed something somewhere.
So, in which part? This A or B?
Yeah, for part A.
Okay.
Okay.
So, you're applying the work energy theorem between points A and B,
Yeah.
which is this.
Mhm.
Wait, I don't understand. Where's the work energy theorem?
Oh, I just said that the
The weight is conservative, but friction is not.
oh, okay. So I can't just add.
Yeah, and the normal force is not mg.
Okay. Yeah, I set the work due to normal force to 0 because it's
Right,
along
but you said that the friction force is mu k, magnitude of the normal force ey, but the magnitude of the normal force is not mg because you're not going on a horizontal rail, you're going on an oblique rail.
Yeah, I set it to 1/2 mg for that reason because I
Oh.
guess I didn't really show my work there, but I just said that since this is negative 1/2 mg ex, so it has to be normal force in the other direction.
Okay. Okay. And the distance traveled is 0.5. So the work of the weight is 0.5 sine 30 sine 60 sine
Yeah.
60, which is radical 3 over 2 mg, and then minus mu k, the work of the friction force, half mg, and then 0.5 without the sine 60. This looks good. So what's the difference?
Yeah, the difference is, I think the answer key says 2.56. I got 2.497.
Did you round before the final answer?
This is my Desmos calculation. So I just put in 0.5 times the 0.4 times 2 kilograms, 9.81 square root 3
Then
over 2.
double it, divide by m at square root. What happens?
And then, sorry, there we go. Okay, that fixed it. I had a 2 instead of a 5.
Oh,
Okay,
okay.
sorry about that. Thank you.
No worries. Okay, cool.
I should have gotten more sleep last night. Yeah, that's a correct answer.
Okay, 5 more minutes to go. For part B, how are we calculating the work of the spring force? Using the potential, right? You're not integrating.
Oh, good point.
Yeah. Yes.
So if I use I know the potential
Mm-hmm.
is, where did I have it? 1/2 K,
Mm-hmm.
and then the deflection.
So you're calculating the work of the spring force.
Yeah.
Yeah, so it's half k, the initial deflection squared minus the final deflection squared.
Okay.
Mhm.
And is that the second part? Is that? Oh, I guess that's.
Yeah, you should square.
So that was that the deflection. Is that the delta x squared?
The deflection. What do you mean by delta x?
Like, because if I'm trying to find the deflection,
Yeah.
is the term that's next to the k, is that the deflection squared?
Right.
Okay.
So the epsilon is the deflection. Yeah, initially deflection
So
is
this is
0.
like this. And
But
then
you
could
should
I
have
set
a
that
minus sign, right?
here.
Yeah, so I'm guessing delta x, that means the deflection
Yeah.
when, like maximum deflection of the spring.
Yeah.
Okay. Done? Same answers?
the W, like work, is equal to the energy, right? So can I do 1/2 mv squared as your energy for that? And set that.
So you're gonna have to do. So you're calculating the work energy theorem between which two instances? For the particle just before it touches the spring and then at maximum deflection?
I guess, yeah.
Okay, so the work energy theorem. So the kinetic energy, call these states B and A. B is at maximum deflection, kinetic energy is 0. A is just before.
Yeah, so
You just calculated VA.
yeah, so then that would be 1/2 mv squared.
MVA squared. Yeah, so minus half MVA squared. And this, on the other side, you're gonna have to calculate the work of the friction, spring force, and weight force as you go from like A to B.
Okay.
Just when you touch the spring and maximum deflection.
Okay. So then this has to be.
What the friction? I already found it's like 0 point, just the same stuff as before.
Okay. And also the weight.
Times epsilon.
Yes.
Spring, do we also need to consider the gravity away from
Yes. Yeah.
I'm not sure if I set it up right.
Okay. So this is the work energy theorem. B is maximum deflection. A is just before you touch the spring. Or what is it? What are B and A? What states they represent? Okay. Perfecto. So TB is 0, TA, VA, just calculate VA. Is equal to the integral of work of the weight, mg sine 60 epsilon, perfect. M minus mu k cosine 60 epsilon minus half k epsilon squared. Okay, you see, this expression is wrong. Yeah.
Well, is it one?
Yeah, this is correct, but this is wrong.
Okay.
Okay, so fix it. So it should be right. The setup should be correct.
Okay, I just correct the friction coefficient.
Yeah. Okay, we need to move on. What's up?
I never really did trying to find the friction force.
Oh, it's still there? This should be very simple. What is it? Is it going like that? Just writing F equals MA. should be able to do this. If you can't pass by office hours, then I'll just make sure you can do this, okay?
Sorry.
Great. I just had I was so almost done.
Okay. So the work energy theorem again is that the change in kinetic energy TB minus TA is equal to the work of all the forces between the two A and B. So then when do we use the work energy theorem versus using the balance of linear momentum? The balance of linear momentum is going to give us differential equation of motion, right? And if I want to relate the motion between two states, then I'm going to have to integrate the differential equation of motion by hand if it's easy numerically, if it's not so easy to do by hand. I'm going to have to integrate, and then I can relate the motion between two states. What the work energy theorem does is that it gives us an equation coming from the balance of linear momentum that relates the motion between two states. So usually when we're relating the motion between two states, we're doing it by hand. We're not integrating a differential equation. We're going to use the work energy theorem. It also has other uses we'll discuss in a bit. So the work energy theorem, I can write it as TB minus TA is the work of all the forces. Now these forces I can divide into two, conservative and non-conservative. So that's the conservative forces plus the non-conservative forces. Okay, so FC are the conservative forces, F and C are the non-conservative forces. To calculate the work of a force, I can go to the definition of the work. What's the definition of the work of the force? The integral of F dotted with dr. Now, for a conservative force, I don't have to go back to the definition to calculate its work and can use the potential energies. So that would be equal to U here, U1 minus U2 or UA minus UB. Now for the non-conservative force, I have no choice but to use the definition of the work of a force to calculate the work of a non-conservative force. Does that make sense? That for the conservative force, I don't have to use the integral definition to calculate the work. I can just use the difference in potential energies. But for a non-conservative force, I have to go back to the work definition to calculate the work of a non-conservative force. Now if I take these two terms to the other side, I will get TB plus UB minus TA plus UA is equal to the work of the non-conservative forces from A to B. Okay? And I can define these kinetic energy plus the potential energy of a system to be the total energy E, the total mechanical energy. So I can write this equation now as EB minus EA is equal to the work of the non-conservative forces from A to B. So again, what is E? The total energy of the system. It's the sum of the kinetic energy plus the potential energy coming from all the conservative forces. So in this form of the work energy theorem, right, they're equivalent. We got this from the first one. In this form of the work energy theorem, we can look at the change in energy of a system. So when is the energy of a system conserved? No non-conservative. What about the non-conservative forces?
Or no non-conservative work.
Exactly. When is the energy of a system conserved? If this term is zero, meaning that the non-conservative forces are workless, or all the forces doing work on the system are conservative. So when is the energy of a system conserved? When all the forces doing work on the system are conservative. If there are any non-conservative forces acting on the system, they should be workless. Under that condition, the energy of the system would be conserved. Can you think of any systems problems we've worked on where the energy is conserved? You can think of previous homework, for example. The projectile motion is without a drag. Is the energy of the projectile conserved? Yes. So as the projectile gains potential energy, it will lose kinetic energy, and vice versa. Okay. What about the simple harmonic oscillator? Is the energy of the simple harmonic oscillator conserved? How come? There's a normal force acting on it, which is non-conservative. It's not doing work, right? It's workless. The spring force is conservative, the weight force is conservative. What about the simple pendulum? Is the energy of a simple pendulum conserved? Why yes? Okay, there's no air friction, but what are the forces acting on the simple pendulum? Weight plus the tension force, right? Which is non-conservative. So there is a non-conservative force acting on the system. So is the energy of the system conserved, of the simple pendulum? Yes, why? What is the work of the tension force? 0. Why? It's perpendicular to the motion, right? The tension force is along ER and the motion is along E theta. Okay, so let's look at the problem set. Where's the rest of mine? Okay, I'll open it up on my computer. So if you look at problem set 11, so problem 1, let us see. Upon its voyage from a space mission, the spacecraft has a velocity of 2,400 kilometers per hour at point A, which is 7,000 kilometers from the center of the Earth. Okay, so there's this rocket spacecraft coming from a space mission. Is the energy of the spacecraft going to be conserved throughout its motion? What are the forces acting on the spacecraft? Yes, this gravitational force up there, Newton's gravitational force, which is conservative. So that's the only force acting on the spacecraft. So is the energy of the spacecraft conserved during its motion? Yes. Now, if a rocket engine is being fired or anything like that, then that would be a different story, okay? So in this system, in problem 2, is the energy of the collar conserved during its motion? Raise your hand for yes. Raise your hand for no. Take a minute, think, discuss. Is the energy of this collar conserved during its motion? What are the forces acting on the collar? Weight, which is conservative, right? Normal force, non-conservative but workless, and P, which is a constant force, which is a conservative force. Okay, so is the energy of the collar conserved? Raise your hand for yes. Raise your hand for no. Okay, good. Any questions? Okay. And the problem you just did, is the energy of the collar conserved? No. Why not? There's friction. Okay. In the next problem, there is no friction. Is the energy of the collar conserved? Yeah. So you can imagine the collar oscillating and will go back up to its initial height and then keep oscillating. Okay. In the next problem, from A to B to C to D, is the energy, there's no friction. Is the energy of the mass M conserved? Yes. Post D, there's friction, it's not. What can you say about the speeds of mass M at points B and at points D? B and D. So I can problem 5, set 11. What can you say about the speed of particle M at A, at B and at D? They're the same. Why? Right, if you apply the work energy theorem between B and D, the kinetic energies is going to be equal to the work of the forces, which is the work of the weight. What is the work of the weight between B and D? 0. Why? what is the work of the weight between B and D? Why is it 0? Right? They're at the same height. So the kinetic energy is going to be the same. Okay. Next problem. The next one is interesting. It's a pendulum. Okay. So it's a pendulum. If we have a simple pendulum, we said that the energy of a simple pendulum is conserved because the forces acting on the pendulum are the weight and the tension force. The weight, which is conservative, and the tension force is workless because the integral of T dot V dt is T E R dotted with R theta dot E theta dt, which is 0. Okay, so for the simple pendulum, the energy is conserved. But what's happening here? The simple pendulum is going to impact, at this point, it's going to impact a fixed pin. So then, beyond this point, the simple pendulum is going to travel like that. Okay. Is the energy of the pendulum still conserved in this motion, given that there's a pin here? Why? It is, but why?
Because the change in acceleration inwards is still perpendicular to it.
Well, kind of. You're close in that the force that's being applied by the pin on the cord over here, but it's being applied at a stationary part of the cord. So the cord is not moving. So what is the work of, what is the work of this force applied at this portion of the cord? 0. Because this portion of the cord is not moving. So we're going to learn this later when we look at rigid bodies. But for a particle, it's just one particle and all the forces are applied on it. For a rigid body, different forces are being applied at different points on the body, right? For a rigid body, different forces are being applied at different points on the rigid body. And different points on the rigid bodies have different velocities, right? So you can think about this phone over here. So this point is fixed, and then all the other points are moving with different velocities, right? So if I look at the force, the work of this force at the pin here, at the pivot, because it's being applied at the point with 0 velocity, then it's workless. Okay? But if I have the phone and I'm moving it like this, then this pivot is not being applied at a point with 0 velocity, then it's not workless. What matters is the velocity of the point of application of the force. What I'm trying to say is that to calculate the work of a force, you need to integrate F dot V dt, the velocity of which point, the point of application of the force. So here, if I look at the work of this force is going to be workless because its point of application is not moving. So if I consider the whole system then, with the cord being massless, the kinetic energy is still going to be conserved. Okay? Or you can just consider this one too, and the tension force is still going to be workless throughout the motion, even as the cord hits the pin. Okay, does that make sense? So the energy of this mass m is still going to be conserved throughout its motion. Okay, and then you can look at the rest of the problems. Okay, any questions? So you'll solve some of the other problems from set 11 in the exercise session tomorrow. Probably we're going to do a quiz about that too, so make sure, well, we review the lecture notes, okay? Any questions? So we have 20 more minutes. What I want to do is introduce the linear impulse, linear momentum equation, and if we have time, angular impulse, angular momentum equation. So let's erase the board here. Okay, if we have a particle of mass m traveling with a velocity v, what is its linear momentum? G is equal to mv. Okay, and we already know about the balance of linear momentum. F is equal to G dot. Right, that's the balance of linear momentum. F equals G dot. If m is constant, then that's F equals ma. Now, the linear impulse linear momentum equation is this. The linear impulse linear momentum equation is the integral of the balance of linear momentum with respect to time. So that's just the integral of f dt from t1 to t2. Okay? So that's the integral of f dt from t1 to t2, which is the integral of g dot from t1 to t2, which is g at t2 minus g at t1, right? So the work energy theorem is derivable from the balance of linear momentum, right? And the linear impulse linear momentum equation is also derivable from the balance of linear momentum. But what's the difference between the two? The work energy theorem. So what are some differences between the work energy theorem and the linear impulse linear momentum equation? Yes?
One is based on time, one is based on position.
Yeah. And then one of them is a vector equation, this one, whereas the work energy theorem is a scalar equation. Now, if you look at the linear impulse linear momentum equation versus the balance of linear momentum, which one is more general, do you think? Why? Which one do you think is more general, meaning that it applies to more situations? Yes?
I would assume this one because of the thing we were talking about, the gradient being, you can only find so many vector equations with a scalar, but you can find any scalar.
Well, I'm talking about the balance of linear momentum versus the linear impulse linear momentum equation, which are both vector equations. Any ideas on which one could be more general? Okay, so let us think together. So this equation, it contains a time derivative, right? Can I always take the time derivative of a function? No, right? I can only take the time derivative of g, which is mv, in which situation? G needs to be continuous and differentiable, right? So can you think of situations where g is not continuous and differentiable? What is it? Yeah, exactly. If you have impact, for example, a ball is bouncing on the floor, then at the impact, there's a sudden change in the velocity, right? So the velocity is going to be discontinuous, and I cannot calculate the acceleration at impact. So when I have impact problems, I cannot calculate the acceleration. I cannot calculate the derivative of the velocity because the velocity is discontinuous. So then, which equation do you think is more general? The second one, the linear impulse linear momentum equation, because it does not assume the existence of the acceleration at all points. Okay? So this one is more general. This term here is called so we already know that this is called the linear momentum. So what is this term here called? Guess? Linear impulse, perfecto. So that's the linear impulse of a force. Okay, so that's the linear impulse of a force F. Okay, under what conditions is the linear momentum of a particle conserved? When is the linear momentum of a particle conserved? Under what conditions? What does it mean for something to be conserved? Yeah, it's constant. It's the same throughout the motion. Do you have an answer? Right, so the energy of a system is conserved if this E quantity is constant. Right, the E1 is equal to A2 is equal to the energy at any time. And here, linear momentum is conserved if G is constant. Then if G is constant, G at T1 is equal to G at T2, then what should F be? 0. If F is equal to 0, then G dot is 0, then G is constant. So if F is equal to 0, the linear momentum of a particle is equal to 0. So you can think of a particle moving in space, no forces are acting on it, its linear momentum is conserved, right? Now, the linear momentum of a particle could be conserved in a certain direction. Okay, so the linear momentum of a particle could be conserved in a certain direction. What does that mean? This means, so in other words, G dot C is equal to a constant. So where C is the unit vector in that direction. Okay. The linear momentum of a particle could be conserved in a certain direction, called the direction C. This means that G dot C is constant. Okay? So when is that the case? I'll take the derivative. This should be 0. The derivative of G dot C should be 0 if G dot C is conserved. So that's G dot C dot should be 0. So this is saying that F dot C plus G. Okay. So if this equation is satisfied, then the linear momentum of a particle along C is conserved. Now if C is a fixed direction, what does C dot equals to 0 mean? Yeah, C is a fixed direction. Its derivative is 0. Then this equation becomes F dot C. Then the condition is that F dot C is equal to 0. Okay? So if F dot C is equal to 0, then the linear momentum of a system along C is conserved. Example, can you think of a motion whose linear momentum is conserved only in a certain direction? Projectile motion. Is the linear momentum of a projectile completely conserved? No, because F is not 0. F is the weight is not 0. But Is the linear momentum of a projectile conserved in a certain direction? Yes. Which direction would that be? The horizontal, because there are no forces acting on the horizontal. Okay. Now, if I consider a direction which is changing like ER and E theta, then I have to be more careful, right? If I consider a direction that's changing like ER and E theta, I have to be more careful because C dot is not zero. Okay? Does that make sense? Okay, one more concept I want to introduce before I let you go for the day is sometimes we're solving a certain equation. So for example, I am playing baseball, okay? I'm playing baseball. The ball comes with a certain velocity v1, and then it strikes the bat, and it goes with another velocity v2, right? I can apply the linear impulse linear momentum equation acting on the ball during this impact. So I can say that g at t2 minus g at t1, that would be equal to the integral of the forces acting on the ball between t1 and t2, right? And if I know v1 and v2 and the mass of the ball, am I able to calculate g at t2, g at t1? Yes. Okay. Now, what would be the impulses of the forces acting on the ball? Yes, that would be the impulse of the weight plus the force from the bat. I'm going to call it the force from the bat dt. Now, this integral, what information do I need to be able to calculate this? The impulse of the weight. Yes, time, right? Because the weight is constant, I can take it outside the integral. So that's just the weight times T2 minus T1. So if I know T2 minus T1, then I can calculate the impulse of the weight. This is basically known if I know T2 minus T1. So now I'm assuming I'm given V1, V2, T2 minus T1. Okay, so then from here, I can calculate the impulse, this impulse, right? The impulse of the force from the bat. Because I know G of T2, I know G of T1, I know the impulse of the weight, I can calculate the impulse of the force from the bat. Does that make sense? My question is, can I then calculate the force from the bat? Can I calculate FB? Do you think it's going to be constant, the impact force from the bat? No.
If it's rigid.
Yeah. If I were to imagine it, I'll say it's like maybe starts slow and it goes up and then goes down. I don't think it's going to be constant, right? So I cannot actually, even though I have the impulse of the force from the bat, I cannot calculate exactly what FP is. But can I calculate the average of FP? The average of the impact force from the bat? Yes. How? Yeah, kind of. So I cannot calculate FP, but I can calculate the average of it. So FP as a function of time, right? Because FP as a function of time is going to look, maybe it's going to look like this, between T1 and T2. I cannot calculate FP as a function of time, but I can calculate FB, the average of it. Okay? So the average of the force is, by definition, it's defined to be the value such that this integral is equal to the average times delta t. So this integral here is the area between FB and the curve, right? So that's the impulse. If I make it equal to F average delta T, then that would be the area of a rectangle whose one side has length delta T and whose other length is F average. So this value would be the average value of the impulse force from the bat during the interval. So in some problems, that's what they do. They cannot ask you to calculate the bat force, the force from the bat, or the impulse force as a function of time during the impact interval, but they can ask you to calculate the average of that force. Okay? That's all for today. Thank you all for coming. I have office hours from 1 to 2, so feel free to pass by if you have any questions. Yes, I'll extend, send me an email, remind me, I'll extend the deadline for you. Yes. So if I forget, I will extend the deadline for you, but if I forget, send me an email, okay?